EEE 145, Chapter 9, Transformer Protection. So everybody, let's go ahead and start talking about transformers. Like always do an introduction and definitions. So first off, what types of transformers do we typically see in the power system? Well, probably the most numerous ones are distribution transformers. Distribution transformers. And these range from the small transformers on the poles you see outside your house to the green boxes called pad mounting transformers in the maybe like in front of the street or something. Or some people would say this is even the transformers in the small substations near the distribution grid. So your step down transformer and substation could be considered distribution transformer, some would say. Others would say anything in the substation are considered transmission level transformers. And they're a little bit bigger. They're there to push a lot more energy than a small distribution transformer. So transmission level transformer, typically like 10 MVA, 20 MVA, maybe 50 MVA if it's really big. They can convert the voltage from a higher voltage to a low voltage for distribution, or they're there to convert from a higher voltage to a medium voltage level on the distribution grid. For example, a 230 kV to 115 kV or a 115 kV to 69 kV. You still need transformer between any two voltage levels so you can have these transmission level transformers. And the last big group is your generator step-up transformers. So generator transformers. So generators typically operate in the 10 kV ranges. And so you want to take that 25 kV or 13.8 kV level and rise it up to grid transmission level, which is like 115 kV or so on. So you need a step-up transformer. So it's a generator transformer. So here we're going to mainly talk about the transmission level transformer. The GSU was kind of covered in transmission side, and the small low distribution transformers, there's not that much complication to them. So here, how do we protect against larger substations? Transformers. You typically have your 87, which is differential, add a T for transformer. You will always need a 50-51 backup in case for some reason the differential fails. And because a transformer is typically filled with oil and there's pressure involved whenever you have any type of closed liquid system, you need to have something called a sudden pressure switch. Sudden pressure switch. This literally measures the pressure of the oil inside the transformer so it doesn't get too high, because if it gets really high, the transformer could rupture. And then not only will you start a fire, you have oil everywhere. It's going to almost pretty much blow up in a giant ball of fire, and then oil is going to seep over to catch fire. It's bad. So sudden pressure switches are pretty much mandatory for any substation level transformer. So that'll be another part that will automatically shut off the system in case something goes wrong. Now, how do we protect small distribution transformers in the poles? I said they're really easy. We don't have to go a lot of details. General rule of thumb, you should put a high side fuse. Okay, so put a high side fuse. And then you just need to make sure it coordinates with the feeder upstream. So high side fuse that coordinates with feeders. Coordinates with, let's say, just to make sure you know, upstream feeders. It's not worth putting a whole protective relay and circuit breaker and all that. It's just, let's get a cheap $100 fuse and stick it up there. And those things should not go too often. All right, so that's pretty much your small distribution transformers and the poles and the little green pad mounted ones at your neighborhood. Let's go talk about substations. So before we go into too much details about the transformer protection, we always need to understand the layout of what we're trying to protect. We know what a transformer is. We've seen that hundreds of times now, but maybe a substation configuration is foreign to you. So let's take a little while to look at this. So for a substation, you typically have high voltage coming in, and these are transmission lines from the transmission grid. So you have your high voltage bus, and then you have a step down transformer, and then you'll typically have your low voltage bus down here. So you have high voltage side, low voltage side, and these are all the feeders on your low voltage side that goes to the neighborhood. Now, if you notice, there's two transformers. So you ask yourself, well, why do we have two transformers? We could have one big one, but we want to split it in half. Obviously, having two transformers is more expensive than having one, but we get a big advantage. And it's if one is offline. What can we do? Because you got to remember, transformers are going to go offline. They're going to break. We got to do maintenance. Do we want to cut a transformer off and black out an entire substation if we only have one transformer? No, we need to make sure we don't lose customers. So if one is offline or one transformer is offline, the other transformer can supply both low voltage buses. Okay. Now, just to show you what we're talking about is, let's say, let's use purple for this one. We have one transformer right here. Okay. This transformer would typically power up these 4 sets of distribution feeders. We don't want to have one transformer do all 8 feeders. We kind of split them off 50% on one side and 50% on the other side. Okay, so we have one over here. That way, if in an unforeseen event, a fault happens, a natural disaster, one of the transformer gets hit, we only lose 50% of our customers, not 100%. So we kind of have it like split between two groups. Now, if for some reason a transformer is out, we want to get the customers back on as fast as possible. So we have something called a tie circuit breaker, which is this piece right here. This is called a tie CB. And a tie is just there to tie together 2 separate buses. So why do we have a tie CB between low voltage bus? It's to keep the low voltage bus separate during operation. Right? We just talked about why, because you want to, in case something fails, you don't want to knock everybody out. You just want to knock half of the people out. But the big factor is, but we can close in the tie CB if one of the transformers is down. So it gives us a lot of flexibility. Now, so in case we lose one transformer, we'll lose half the customers, and then probably within 10 seconds, the operator can know what's going on, and he'll remotely close in the tie circuit breaker. So then one transformer can feed all 8. One transformer can feed all 8 feeders. So we're kind of in emergency mode, but at least all the customers are back online. Okay. This is a very common substation setup you're going to see is the 2 transformer system. Okay. Now we see how a substation is built. Let's talk about protecting it. So by far, the transformer is the most expensive device in the substation. So it needs the most attention. Now, also is the transformer, when a transformer fails, it's a big deal because that causes the most amount of problems in the substations. So if a transformer ends up failing and we have a fault internal to the transformer, we need to disconnect it immediately. So disconnect the transformer from the system. That's the #1 goal. Otherwise, the transformer is going to feed a fault, and you'll eventually black out the whole system if you leave it on too long. Now, so that's what happens if we have a fault internal to the transformer. What happens if we have a fault external to the transformer? Let's say it's on a feeder. Let's say it's on a transmission line. Let's say it's the next substation over. We don't want to disconnect our transformer when we're not the problem, right? That's protection 101. only disconnect the minimum amount of equipment needed. So we need to make sure we have the ability to ride through external faults. What other factors do we need to protect? So we talked about sun pressure. That definitely needs to happen. And another thing that's unique to transformers, because they're big devices, they're pretty much a gigantic inductor, lots of magnetic coils that needs to be energized. You have a lot of transient conditions. Anytime you deal with something with a lot of wires wound up, like motors, generators, transformers, you're going to have transient issues you're going to have to deal with, and they're quite big in transformers. So these are kind of extra things we need to deal with besides the fault current that we'll talk about this week. All right, so now let's mainly talk about the transformer protection from fault current, right? Because fault currents are typically the most damaging thing you'll ever encounter. So the tried and true 87 differential is by far the best type of relay we use because it's the fastest. It can detect internal faults versus external faults. If you ever have a chance, always use a differential. That's my philosophy. So we're gonna have something called an 87, and we could put a T if you want here to signify transformer. Some people do, some people don't. I'm gonna put a T just to make sure I know it's a transformer differential. And then we need to put our CT somewhere. So remember, the rule is whenever you put CTs, you want to encompass the transformer, but if possible, you want to wrap around the two circuit breakers responsible for the transformer. So always wrap the breaker in to our zone, like so. So if you remember, the CTs are the borders of our differential zone. So it's the same thing on the right-hand side transformer. We have a CT on one side, wrapping in the top breaker, another CT wrapping in the bottom breaker, and both of these wires will lead to 87T. So if you notice, for this particular setup, we're going to need two differential relays, one for each transformer. Okay, so say one 87T per transformer. And then which relay will operate as a differential zone? Kind of gave it away right here, but we'll say 87T. This is a differential relay. I'm telling you right now, the industry is pretty much moving forward. If you can afford a differential relay, it's pretty much the way to go from here on out. So get used to it. Okay. So that's the very basic. Let's get a zone up and running for the transformer. Let's protect it. Now comes a little bit more complications. Unlike a basic differential zone where current goes in and current goes out and they're the same, transformer voltage levels complicates it because current in does not equal current out. And that's a problem for the differential relay because it runs on the principle current in equals current out. Remember, there's a turns ratio involved. So the turns ratio, there's a difference in current from input and output. And if you remember that it's a straight ratio. If you have 10-to-1 transformer, then your current is going to go up by 10. If you have a 5-to-1 transformer, your current will increase by 5, right? So you just have to take it into account whenever we design our system. But it is one more complication that we need to remember. Another one is typically delta versus Y connections. Transformers are typically delta Y, especially on these step-down transformers. So if you remember, when you go delta to Y, there's always a 30-degree phase shift. And if you don't take this into account, your relay will not read the correct current. Remember, current, when you say currents are equal, it's not just magnitudes. They have to have the same magnitude and the same phase shift. So a 30-degree phase shift could It's not guaranteed, but it could trip a differential offline, right? So we're gonna have to deal with a 30-degree phase shift. Lastly, you have voltage control and regulations. You have something called LTCs, which is load tap changing transformers. So this is an automatic process. And just to give you the 30 seconds version of it, a transformer typically has a hard turns ratio that's wired in, but we could put an LTC to kind of change the tap on the secondary side and ultimately change the turns ratio. So it can automatically change the turns ratio. And the limit is typically plus or minus 10%. It's not that much, right? And the reason why we have this is the voltage can change during the day. When the system is heavily loaded and we're running our houses a lot, the voltage on the feeders tend to dip down a little bit versus the middle of the night when no one's running anything, the voltages kind of spike up. So to make sure we have a constant 120 volts to the customers at the substation, we might have to go plus or minus 10% and kind of every 5 minutes monitor it and maybe click up or down a 0.1% difference just to make sure the customers have a constant 120 volts or as close as possible. We don't want the customers to wake up at night and have like 135 volts on their system, on their output or electrical output at their house, because you're going to burn up all their equipment. You also don't want the customers to be at like 5 o'clock in the afternoon, want to run their AC and the voltage dips down to like 90 volts, because then things will shut off. So LTC is there to make sure we don't get to those extremes and stay roughly within that 120 voltage range. The problem with the LTC is it's another piece of device that changes the turns ratio. And by changing the turns ratio, it changes the current in versus current out rule and makes our life a little bit more difficult from the differential protection standpoint. So these are kind of three major things that we need to design, and we need to make exceptions, or we need to design our system to accept these burdens. Okay. So let's go through and ask ourselves, well, how can we mitigate these problems and fix it to ensure that the differential relay will work? Because we definitely want to keep the differential relay. So the first thing is the CT ratios. So because we know a transformer has a 5-to-1 ratio, we know the current's going to be different by a factor of 5-to-1 in this example. The easiest way we can change things is to make sure the CT ratios are different. So remember, I always want to make sure I have roughly 5 amps flowing in my secondary circuit as much as possible. So if I have 300 amps coming in on I1, I can choose a CT ratio to make sure I have 5 amps secondary. And that CT ratio will be 300 to 5 to make sure we have 5 amps secondary. So I can put 300 up here. Okay. We could calculate I2, same idea. Now here's one. So we know we have 300 amps on I1. What's I2 going to be? Well, we know it's a 5-to-1 ratio. So we know I2 is going to be 5-to-1 times I1. Okay, this is your standard turns ratio. And this will be 5 times 300, which will be 1500 amps. So we know that the current coming out of transformer on the low voltage side is 1500 amps. And we want 5 amps secondary, right? So let's make sure this happens. Well, it's easy as 500 amps to 5 amps is a 1500 to 5 CT ratio. Okay, so we could just go down here and say, let's make sure our CT is a 1500 to 5 CT. So you can see, normally when we do differential, we want to make sure the CTs are at exactly the same ratio, so the current is equals current out. But a transformer, we don't want the CT ratios to be equal. We want to make sure the CT ratios are off by the same ratio that the turns ratio of the transformer is, right? So they're kind of pairing together. And that's one way we could fix the voltage variations and that quote unquote cancel the turns ratio effect on the current. Because in this particular setup, we have 5 amps coming in and 5 amps going out. the operating current in the relay is 0. So this is a perfectly balanced differential relay, despite having a vastly different input and output current. So the magic is the CT ratios. That's what fixes a lot of things. So that's the first problem. The second problem was the delta to Y 30-degree phase shift. Now, this has always been a big problem in the power industry. Luckily for you, digital relays are the majority of the system now. And with digital relays, we kind of solved this problem inside the microprocessor of the relay. So we don't need to worry about 30-degree phase shift on the system anymore. We could just, it's a setting change. A setting in the relay we program. Relay we program. So if you ever go to SCL 387 relay, there's going to be a transformer page, and you can literally tell the relay, hey, we have delta high side, Y low side, and the relay is smart enough to fix a 30-degree phase shift for us, so we don't have to do any changes ourselves. So with this, to make our lives easier, the CTs, we could configure Y to Y connections for the CT and have a delta to Y, and the digital relay will counterbalance the phase shift. Okay. So I would even say it fixes the phase shift in the relay. Okay. Now, if you are very unfortunate to have to go to a system where you don't have a digital relay and you're stuck with mechanical relays and they refuse to upgrade, and if I were you, I will push really hard to upgrade to a digital relay. But there could be a point where somebody's going to say, no, I absolutely refuse. I want to live in the 1960s. Okay. Or you go out there and you see mechanical relays. The old school way is to use a delta to Y CT connection. And the rule is you would, whatever the transformer configuration is, the CT configuration will be opposite of the transformer one. So if it was a delta connected side, you put a Y connected CT. If it was a Y connected side, you put a delta connected CT, and they would cancel out the phase shift between each one. Okay. Again, this is a very old system. 95% of the system in today's world is digital relays, and we do Y connected CTs across a whole system. But you might find an archaic 1960s relic substation. Don't be super amazed, or don't be shocked if you see a delta connected CT on a Y delta transformer. Okay, that's all I want to point out. Okay. The next part is the load tap changing transformer problem. Remember that plus minus 10% change in turns ratio. What can we do? So we need to figure this out in the relay. There's no amount of CT configuration that's going to fix a changing target that changes the turns ratio every 5 minutes. So the relay needs to have a setting. Have a setting to handle the deviations. Deviations of turns ratio. I mean, that's just a matter of fact. So we'll talk about what inside a relay can we do to absorb that plus or minus 10% error we're going to get, because the turns ratio can fluctuate a little bit. Okay. So all three of those things we talked about, that's all it works majority of the time. There's, unfortunately, in real life, turns ratios are not perfect. CT ratios are not perfect. It's very common that we're going to have something called CT mismatch. You've noticed by now, CT ratios come in standardized sizes. like 100 to 5, 200 to 5, 300 to 5, 400 to 5, maybe 250 to 5 if you're lucky. You can't get a CT that's like 167.4 to 5 at all, right? So sometimes you might have a very weird turns ratio. For example, here, if we have 150 kV system to 12.47 kV system, we have a turns ratio of 9.22 to 1. There's no way you could go to CT manufacturer and say, I want a 9.221 CT. They're going to look at you like you're funny. They're going to say you have the option of 250 to 5, 300 to 5, 400 to 5. We're not going to custom wind it for you. And so you have to just do your best guess. So here we have a system that we designed with a 250 to 5 CT on the high side and a 2005 CT on the low side. Just from looking at these numbers, you know these are not a perfect 9.221 ratio. So we're going to have some error in the CT readings or the secondary current. So let's kind of look into that. How can we calculate secondary currents going through the relay? Well, the easiest thing is you got to find your current. So first we need to find our main current flowing through the system. This is your low current, maybe high load. This is always going to be equal to your MVA divided by square root of 3 times your KV. I've wrote this about 30 times in this course now, so this should be second nature to you. Now, once you find your main low current, you can find your secondary current. So this will be your low current. Our secondary current is going to be what's flowing into the CT. Oh, sorry, what's flowing out of the CT right here. That's your I secondary. Now, how do you figure that? I secondary is going to be your low current through your CT ratio. Now, you're going to have two sets. You're going to have a high voltage side and a low voltage side. So this is your high voltage secondary current. This is going to be your low voltage secondary current. And they're going to be different because of the different turns ratios of the transformer and the CT ratio. So because they're going to be different, we need to calculate that, and that's called a mismatch ratio. So we will take the secondary current and see what's the difference between the high voltage side and the low voltage side. And this is going to be a ratio like 0.9, 0.87. You know, typically this hopefully should never be above like 0.7 to 1.3, right? If you have anything higher than this, you got some really, you got some very badly matched CTs, okay? But it gives us a way to figure out how severe we are. And this is very important because we need to fix it. So now we know how off our CTs are. Let's go talk about undoing the problem. So now we know our mismatch. What we can do is have kind of secondary CTs in the relays called taps. So we use relay taps to correct the CT mismatch. So think about taps as a secondary CT to correct any small error, right? And they're built into the actual relay itself and their settings. So you see how you have this HV tap, low voltage tap, and a microprocessor based relay, you can literally just plug in any number, right? So if my mismatch is 0.8, I could plug in 0.8 for one and 1 for the other, and it solves it, right? And how do you know what your high voltage tap and low voltage taps are? Your mismatch, which we calculated from the previous page, is a combination of your high voltage tap divided by your low voltage tap. So for example, if your mismatch was 0.8, you could then choose your high voltage tap and your low voltage tap, whatever ratio you want. I would probably choose 0.8 to 1. That's the easiest one, right? But technically you could choose any ratio of that. And so in my relay, I'd say, okay, well, high voltage tap is 0.8, low voltage tap is 1.0, and that should correct any imbalance you had before, and then the differential relay will act correctly. Okay. So with that being said, we kind of went over a couple of main points about choosing the correct CT ratios and then being a little bit constricted by the design of CTs and then having a mismatch problem. And then the second step would be finding your CT taps, your relay taps to then correct this mismatch. So here we typically take our 15-20 minute break. I want you to do some exercise in the middle of class. Let's go ahead and do a differential design. So we have a differential zone. We have a transformer, which is 115 kV on the high side and 12.47 kV on the low side, and 25 MVA, right? So you should go ahead and ignore this. This is not a 5-to-1, okay? Here, your first step is let's design and size the correct CT configuration. So you have this is a set the manufacturer's given to you. They have 100-5, a 200-5, 300, 400, 600. These are the only CT ratios he can offer. I want you to pick the correct high voltage CT side. Remember, you have 25 MVA, you got your 115 kV. You could figure out your low current first and then select your CT accordingly. Same thing for your low voltage CT. Figure out your low current on the low voltage side and choose the best CT ratio. Remember, we want to stick to that 5 amp level, but we don't want to go over the 5 amp. Okay. So pick the closest one you can. Once you got those two picked, pull them over here. And then we're going to have to figure out our mismatch for these CTs. So here, you need to figure out what's your mismatch ratio. You have your primary current, your secondary current. You're going to have to figure those two out. Once you figure out your primary, secondary current, then you could figure out your CT mismatch. Okay. And then lastly, once you know you see your mismatch, figure out your relay tap settings for your low voltage and high voltage side to program in the relay to fix a mismatch. So you have a near perfect differential or near perfect current going into the differential relay, and it won't trip off of, non-ideal CT ratios. Okay. So let's go ahead and take that 15-20 minute break, and we'll come back a little bit, see what you guys design. We'll talk to you in a little bit. Okay, welcome back. So let's go ahead and check out this differential design problem we had. So remember we said that we need to find a high voltage CT side. So here we have I1, which is a low current is 25 MVA divided by square root 3 times 115 kV voltage. This is equal to 125.5 amps. Unfortunately, we don't have anything that close to 125, so we have to stick to a 205 CT. On a low voltage side, we have I2 is equal to 25 MVA divided by square root 3 times 12.47 kV. That's your low current, 1157 amps. That's actually really close to 1205, so we could pick 1205. So you can already know, because I2 has a very close ratio that's almost perfectly matched, but I1 is very far off, you're going to have a pretty bad mismatch right here. Okay. If they're both near perfectly aligned, your mismatch would be almost non-existent. So let's go ahead and see how bad it is. So here we go, let's figure out our mismatch ratio. So you always find the secondary current of both sides. So I secondary for the high voltage side, this is 125.5 amps divided by the CT ratio of 40. And 40 is 200 divided by 5, FYI, right? So you figure out that CT ratio, that current, and that's 3.138 on the primary side. And so, maybe just to add this in, this right here is 3.138, okay? Now on the low voltage side for the secondary, we have a 1157.5 amps divided by 240, which is 12, our 1205 ratio. That's 4.823. So 4.823. Remember, we only have roughly 5 amps or right below it. So on the low voltage side, 4.8 is very close to 5 amps, but on the high side, 3.13 is kind of far from 5 amps. It's not terrible, but it's not ideal. So we definitely have a ratio mismatch. So our mismatch was 3.138 over 4.823. You could just carry that over. Our mismatch is literally a high voltage tap over a low voltage tap. The easiest way for a digital relay is just to take those two numbers and slam them into the actual tap setting. So because we know our secondary current on a high voltage side is 3.138, a high voltage tap of 3.138, our low voltage tap is 4.823, which corresponds to the secondary current on the low voltage side. And the relay smart enough to do the division for us to find the actual ratio. So from this point on, this is how we correct all that CT mismatch, and your at least based on the CT ratio chosen, your relay should act pretty good and accordingly now. Okay. So that solves the CT mismatch. The one problem though is, there's always some noise in the system. Something doesn't work perfectly all the time, even if we have the taps set. So we need another layer to deal with CT mismatch, or maybe one CT operates a little bit wonkier than the other, right? We need a second layer. And another layer we can use is called restraining coils. Okay, so like I say, in a realistic world, operating current will never truly be 0 amps, right? We must build some tolerance in the differential relay. So somehow smart enough a long time ago would say, hey, why don't we have a second coil right here called a restraining coil? And we'll have current flowing through it, which is the same current flowing through the relay and the operating coil, except this restraint coil will try to stop the relay from acting. Stop the relay from acting. And acting is tripping in this case. So the restraining coil, restrains the relay, but you don't want to use the same word twice. So if the relay wants to trip because they're very small current, the restraint coil will actually lock it in and stop it from tripping. Okay. So what happens when current flows through the restraint coil? It actually holds back the operating coil. It physically holds back the operating coil from tripping. Okay. And so if we have that, maybe we have 0.05 amps or a few, maybe a 100 milliamps flowing through, the restraint coil will stop the operating coil from just blasting the circuit breakers open for even the smallest difference. Okay. Now the question is, how much are we going to restrain? Are we going to restrain everything? Because then it won't trip. So there's some middle ground. And this is where we have to start programming the relay. So the idea is the restraining coil, again here, has both currents flowing through it on both sides. Okay. So you're going to have some amount of current flowing through here, some amount of current flowing through here, depending on which way the current's flowing. We're going to call this IR1, IR2. They're both going through the restraint coil. So the restraint coil would take the average of both of these, because the restraint coil, if you see, is split down the middle. So half of the current flowing through one way, half of it's flowing through the other. So we roughly take the average. So you take the absolute value of both currents, because the restraint coil doesn't matter which way the current's flowing, positive or negative, it'll still try to stop us from operating. And we'll take the average of those two. Okay. And then we'll compare that to the operating current that actually flows through the coil. So this is I operating. Okay. So if we take I operating and then we divide that by I average, which is what their restraint coil is going through, we're going to get a percentage. And this is called the percent restraint. Sorry. And this is pretty much exactly what the relay calculates, right? Percent restraint. And so what the relay will check is it's going to say, hey, if I operating is much, much greater than I average, that means there's something wrong, right? There is an internal fault. Because remember, when there's an internal fault, so right here, this is a fault side. If you've seen so far, the operating current when there's an internal fault is huge. It's like 100 amps or 670 or 80 amps. So it's much higher than the current going through the actual normal relays itself, the CTs. So you'll have a very high amount of operating current, and the average current going through the restraining coil will probably be lower. And so this is an easy check for the relay. And then we can make some rules. Like so, therefore, let's make a rule if this ratio I operating over I average, which is a percent restraint, if this thing, let's say, is greater than 40%, we trip. Okay, that could be a rule I put in. And just to show you where does 40% lie, it's this, you could graph it here, is this line right here. So notice it says 40% right there. If we do this calculation of operating current divided by average current and we land on this fault side right here, then we're going to trip. If we're underneath it, we're going to be in the restraint area and then we won't trip. Okay. So that's the calculation that relay does. Now let's see it in practice to kind of make sense of all the math, right? So here again, we have operating coil and restraint coil. And I give you I1 and I2 just to make the numbers a little easier. So let's figure I operating. So the I operating is what's in the coil right here. Okay, so that's this current. Okay, let's color code this. Okay, so I operating is equal to I1 minus I2, always takes the difference. In this case, is 50 minus 40 amps. And remember, this is an external fault, so the fault's outside. That's why it's going to be relatively low. It's 10 amps. Right? Now, let's figure out the restraint current. So remember, the restraint current is what's flowing through this coil right here. So the average of the two currents going in is going to be I1 magnitude plus the magnitude of I2 divided by 2. And in this case, this is 50 and 40 amps. So 50 amps plus 40 amps, you average them out, that's 45 amps. Okay. So already you can see that the operating coil is quite a bit less than the average, the restraint coil. So let's go ahead and see what the results are going to be. Well, we have remember, we checked the ratio I operating over I average. It's 10 amps over 45 amps. So what's the percentage we're at? We're roughly about 22%. Let's compare it to what our setting is. Our setting, as you see right here, is 30%. So we're going to take 30% and compare it to 22%. Are we greater or less than? We are less than, right? So that equals a no trip condition. Okay, remember that's a criteria. If we're underneath that 30%, no trip, this is an external fault. We don't have to deal with it. If we go over 30%, then we trip out. Okay. Now let's do the same thing. And let's say there's an internal fault. Okay, so the fault is inside our zone now. So let's go ahead and write faults right here. Okay. Let's do the same calculation that we did before. So let's go. Let's draw our coils again. So we got our operating coil right here. So I operating, be careful because now the currents are both going into the fault, right? So one current is going to be negative. And let's say the current is a little bit different this time. So I operating is I1 minus I2, which in this case is 50 minus a negative 30, which is equal to 80 amps, right? So immediately you can see alarm bells, 80 amps into the coil is definitely fault level. Something's wrong. But let's double check to make sure the restraint coil is not going to block us. Okay, so let's go ahead and do a restraint coil. Remember, that's this one right here. So I average is equal to I1. Remember, we always take the average of the magnitudes of both currents going into the coil. And this time is 50 plus 30 over 2, which is equal to 40. And lastly, remember we have our restraint. Oh, that's the error. It should be 30%. Sorry, didn't change that. So let's write that 30%. Okay. So 30%. Let's check those numbers. I operating over I average. This is equal to, in our case, 80 amps over 40, which is 200%. So immediately I know 200%. That's way, way, way too much. So this is much greater than 30%. So this is a solid trip. Okay. So that's pretty much differential relays with that restraint coil put in, right? So almost every relay in today's world is going to have the restraint level because you're going to have some of those variations, right? But the nice thing is, even if there's a variation outside our system, internally we're fine because the internal fault will always overcome the restraint unless you have like, I mean, unless you put like 100% restraint or something insane like that, right? You typically won't see a restraint for the CT differences to be more than 30 or 40%. Even those are pretty extreme. Okay. So just to sum everything up we talked about today, because we did go over a lot, is transformer differential settings. They're more complicated due to a turns ratio they have to fight. The delta to Y connections, which offers a 30-degree phase shift. CT mismatching, because we won't get those perfect CT ratios we calculated. We're at the mercy of the manufacturer. LTC operations will always kind of change that turns ratio a little bit. So we have the restraint coil to help LTC operations and CT mismatch. We got tap settings for the CT mismatch itself. The digital relay can fix delta to Y connections, and the turns ratio is always fixed by choosing different CTs on the high side and low side of the transformer. So when you're in front and computer, you need to program your settings. Just remember, total microprocessor, delta to Y configuration of transformer. Make sure you have your tap settings in your relay correct to fix the CT mismatch. Standard pickup coil for your differential settings will be about 0.25 amps to 0.5 amps. You want this pretty sensitive. Percent restraint, typically 15% is on low end, up to 60%, really depending on the transformer and what you need to protect. Okay. So we'll go ahead and call it for today. We did a lot of work. We're going to come back next time. We're going to talk about more details on transformer protection. Okay, so thank you for showing up and hope you guys have a good day and we'll catch you later.